Welcome back to Examify's IGCSE Physics Revision series. In this session, we will explore Unit 6, Space Physics. Our journey takes us from the Earth's daily motions and their solar system, all the way to the life cycles of stars, galaxies, and the expanding universe. By the end of this revision, you will not only recall key definitions and formula, but also understand the concepts behind them, which is essential for exam success. Let's begin with Chapter 22, the Earth and the Solar System. The first topic for the day is about the phenomena of day and night on Earth. The Earth rotates once on its tilted axis every 24 hours. This rotation causes different parts of the Earth to face the Sun at different times, giving us day and night. When one hemisphere receives sunlight, the other experiences darkness. This cycle repeats endlessly, creating a rhythm of daily life. Remember, rotation causes day and night, while revolution causes the seasons. Next up, we have the seasons. We know that the Earth revolves around the Sun, completing one orbit every 365 days, or simply 1 year. But the reason for the seasons is not the distance from the Sun. Instead, it is a tilt of the Earth's axis, about 23.5 degrees. When the northern hemisphere tilts towards the Sun, it receives more direct sunlight, leading to summer. When it tilts away, it receives weaker sunlight, giving winter. The southern hemisphere experiences the opposite pattern at the same time. So the key fact here is Earth's axial tilt creates the season. And that brings the closure to Earth. Wait, we have not seen the Moon, the only natural satellite of Earth. Now let's explore the phases of the Moon. The Moon both rotates on its axis and revolves around the Earth. These two motions take about the same time, roughly a month. As a result, the same side of the Moon always faces the Earth. From Earth, we see changing shapes of the Moon, called phases. Starting from the new Moon, where no lit portion is visible, the cycle continues to waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, last quarter, and waning crescent, before returning back to the new Moon. This entire cycle takes about 29.5 days. Or roughly we can say a month. The next concept is very important to understand in this chapter, the average orbital speed. Planets travel in orbits around the Sun. To calculate the average orbital speed of a planet, we use the simple formula, speed equals distance divided by time. For circular orbits, the distance is the circumference of the orbit, which is 2 pi r. So the formula becomes V equals 2 pi r divided by t, where r is the orbital radius and the t is the time for one orbit. For example, Earth's orbital radius is about 1.5 times 10 to the power of 11 meters. And its orbital period is about 1 year. Substituting these values gives an average orbital speed of about around 30 kilometers per second. You might have learned this concept in your lower grades. It's the solar system structure. The solar system is made of of the Sun, planets, moons, asteroids, comets, and other minor bodies. The Sun contains over 99% of the system's mass, and its gravity holds everything in orbit. The first four planets, Mercury, Venus, Earth, and Mars, are small and rocky, often called as terrestrial planets. The outer four, Jupiter, Saturn, Uranus, and Neptune, are much larger and mainly gaseous. This division into rocky and gaseous planet is a key feature often tested in exams. Previously, in the orbital speed concept, we assumed that all the orbits of the planets were circular. But here's the fun fact. Not all orbits are perfect circles. According to the Kepler's first law, planetary orbits are elliptical, with the Sun at one focus. This means the planet is sometimes closer to the Sun and sometimes further away. At the closest point, the planets move fastest. At the farthest point, the planet moves slowest. This change in speed is explained by the conservation of energy. When gravitational potential energy is least, kinetic energy is greatest. In this slide, we have some planetary data and interpretation that has been done by scientists. The orbital distance. The larger the orbital distance, the weaker is the gravitational attraction towards the Sun. And then the density. The lower the density, the larger the size of the planet. Gas giants have low density and large volume. Surface temperature. Generally, the farther away a planet is, the cooler the range of the surface temperature the planet has. The color of the surface and atmosphere can affect the temperature. White and black surfaces affect radiation. Planets without an atmosphere cannot retain heat, heating up and cooling down very quickly. Then we have the uniform gravitational field strength. The greater the gravitational field strength on the surface, the greater the mass of the planet. Previously, we saw how to categorize the terrestrial planets and the gas giants. Now we will see the reason behind why they are known as terrestrial and rocky, and why the others are known as gas giants, or mainly they are formed by gases. According to the accretion model, the solar system formed from a huge cloud of gas and dust called a nebula. Gravity caused the nebula to collapse and spin into a disk. The small particles stuck together, forming planetesimals, then planets. Closer to the Sun, rocky planets formed because high temperatures prevented the gases from condensing. Farther away, gas giants developed as ice and gas accumulated. Now let us explore the concept of gravitational field strength. A gravitational field strength is defined as force per unit mass acting on an object in that field. The gravitational field strength of a planet or star depends on two things. Mass. The greater the mass, the greater the field strength on the surface of the planet. And then the distance. The larger the distance from the planet, the weaker the field strength. The Sun contains most of the mass of the solar system, which is why it has the strongest gravitational field strength and why all the other planets are orbit around the Sun. The last concept in this chapter is the light year. To measure huge distances, astronomers use the light year, the distance light travels in 1 year. Since light speed is 3 times 10 to the power 8 meters per second, Multiplying by the numbers of seconds in a year gives about 9.5 times 10 to the power 15 meters. For example, the Sun is about 8 light minutes away from the Earth, while the nearest star, Proxima Centauri, is about 4.2 light years away. With that, we have completed chapter 22. So, well done. And now we will move on to chapter 23, Stars and the Universe. This is not only the final chapter of Unit 6, Space Physics, but also the last chapter in our IGCSE Physics Revision series. In this chapter, we will explore the fascinating life cycles of stars, the structure of galaxies, and the evidence that the universe itself is expanding. We will connect the physics we have learned so far with the grandest scale of all, the cosmos. As this is our concluding chapter, it's your chance to consolidate everything we have studied, from the tiniest particles to the largest galaxies, and be fully prepared for your exams. The first concept in this chapter is the Sun and the stars. The Sun is a star, an enormous ball of hot gases, mostly hydrogen and helium. Like other stars, it generates energy by nuclear fusion in its core. Fusion converts hydrogen into helium, releasing massive amounts of energy, which balances the inward pull of gravity. This energy radiates outward as heat and light, sustaining life on Earth. The Sun is one of the billions of stars in our galaxy, the Milky Way. Having learned about the Sun and the other stars in our Milky Way galaxy, we need to know how they form. Now we will move on to the life cycle of stars and investigate this process of forming stars. Stars form in vast clouds of gas and dust called nebulae. Gravity pulls the material together to form a protostar. When the temperature and pressure in the core are high enough, nuclear fusion begins and the star enters this main sequence phase. If the star has a similar mass to the Sun, it remains stable for billions of years. Eventually, it expands into a red giant, then sheds its outer layers to form a planetary nebula. The remaining core cools as a white dwarf. If the star is more massive than the Sun, the sequence is different. After becoming a red supergiant, the core collapses violently into a supernova. Depending on the remnant's mass, it becomes either a neutron star or a black hole. The black hole often occurs when the gravitational pull is really strong, such that it can even absorb the light. Our galaxy, the Milky Way, is a spiral galaxy, about 100,000 light years across, containing hundreds of billions of stars. But the Milky Way is only one of the billions of galaxies in the observable universe. The scale of the universe is beyond imagination, but important exam facts include: galaxies contain stars, stars from sun systems with planets, and the universe consists of countless galaxies. The upcoming concepts from now are presumably new and important to remember. The first is the redshift. A key observation in astronomy is the redshift. Light from distant galaxies is shifted toward longer, redder wavelengths. This means those galaxies are moving away from us. Edwin Hubble discovered that the further away a galaxy is, the faster it recedes. That is, the faster it moves away from us. This relationship is called the Hubble's law. It shows that the universe itself is expanding. The next concept is the cosmic microwave background radiation, in short CMBR. Further evidence for the Big Bang comes from the cosmic microwave background radiation. This is a faint microwave radiation detected uniformly across the sky. It is believed to be the cooled remnant of the intense radiation released shortly after the Big Bang, now stretched into the microwave region by the expansion of the universe. The cosmic microwave background strongly supports the theory that the universe began in a hot, dense state. And now we have reached the last topic of the day, Hubble's constant and the age of the universe. The Hubble's constant measures the rate at which the universe expands. It is the ratio of a galaxy's recession velocity to its distance. If we take the reciprocal of the Hubble's constant, we obtain an estimate of the age of the universe. Using current values, this works out to roughly 14 billion years. This matches independent estimates from star clusters and radioactive dating, giving us confidence in our understanding of the cosmic history. And with that, we have reached the end of Unit 6, Space Physics, and indeed, the very last chapter of the entire IGCSE physics syllabus. If you have watched all the way to this point, take a moment to appreciate your journey. You have made it through every concept, from motion and forces to energy, waves, electricity, magnetism, and now to the stars and universe itself. That's an incredible achievement. Remember, revision is not just about memorizing facts. It's about understanding the concept crystal clear. And the effort you have put in here is already a sign of your dedication and determination. So, on behalf of Examify, I want to thank you sincerely for staying with us through the entire series. Your commitment has brought you this far, and with the continued practice, confidence, and belief in yourself, you are well on your way to success in your IGCSE exams. Congratulations for making it this far. Now, if you're looking to take your prep to the next level, we have got something special for you. For just $15, you can unlock lifetime access to our premium boardroom sessions and mock paper bundle. This upgrade gives you exclusive boardroom style walkthroughs of tough questions, full mock exam papers with step-by-step solutions, and insider tips that will sharpen your exam technique. So if you have enjoyed this free revision series and want that extra edge for your exams, check out the link in the description to upgrade today. Thank you for watching and best of luck with your IGCSE exams.